So for part one of electrostatics and conductors, let's look at the range and types of good conductors and not so good conductors. In the conduction of current through a material, if it's made up of normal matter, which most is, you have atoms and molecules, there's a wide range in their ability to conduct current. So in terms of charge transport, we usually describe these things as a good conductor, so for example metals, something in between, which are semiconductors or very poor insulators, and a non-conductor, which we call good insulators. Why materials conduct charge very well in terms of being a good conductor versus not so well depends on the atomic structure that is being made to build these things, and it's a quantum mechanical type of system, and so this leads to structure of the materials, and it also leads to a temperature dependence in terms of their ability to conduct. And so because of thermal internal energy changes with temperature, it can affect the conductivity. Well, band theory is a way of explaining conduction in many materials, and the bands are the conduction band and the valence band. Now normally the valence band is full, and so there are electrons that are bound into the solid right here. The conduction band is where if you have charge, and in particular electrons, if you apply an electric field, they can move through the material. Now this is energy and not space. So if you take some electrodes, so for example just these, say, plates of metal, and you put a sample in here like this in contact with this sample and the electrodes, and apply a voltage across here, if you have a wide band gap material, you'll have very little current. If you have a metal, the conduction band and the valence band actually overlap, so it takes no effort for electrons to get into the conduction band, and so therefore you have motion of charge as soon as you apply a potential across here. Semiconductors have a small band gap, so they're just like insulators, except they have a band gap on the order of a few tenths of an eV to 1 or 2 eV typically. There are some wider band semiconductors. Okay, so just remember that this is not space, this is energy, and over here we apply voltages across the conductor and determine the magnitude of the current, for example, as a function of this applied voltage. So let's take a look at this table here. This is the resistivity, which we call ρ, and this is the conductivity, which turns out to be 1 over the resistivity. So if you have a very resistive material, you have a very poor conductor. And likewise, if this is very small, then you have a high conductivity. And this is the way the symbols relate, just by taking the inverse. Well, if you look here, we have metals, we have alloys, and semiconductors, and insulators. And here's some names associated with those types of materials. If you just take a look at conductivity, this range of conductivity for metals puts you in the ballpark of 10 to the 7th, and the units are inverse ohms, inverse meters. Alloys tend to reduce the conductivity slightly, but not very much. So these are on the order of 10 to the 6th. Semiconductors, because of that band gap, are less conductive, and so they have values ranging from about 10 to the minus 3 to 10 to the 4th. And then finally, insulators are very poor conductors, and they have conductivities in this range here. Fused quartz, which is silicon oxide, fused meaning that it's glassy, has one of the lowest conductivity values, which makes it an extremely good insulator. Glass, by the way, I said this was glassy. This is pure SiO2. Glass has all kinds of things in it depending on the manufacturing, but typically it has sodium and other ions in the material. To tell you the truth, the thing that it buys you is a lower melting point, so it's a lot easier to work with than fused quartz. So in terms of these typical normal good conductors, we're talking metals. Here's some of the best: gold, platinum, silver, and copper. The charge carriers in these materials are electrons, and that's such that you have a finite DC resistance at finite temperatures. So above T equals 0, you have values where you can get current through that. So really what we should say is that above T we have T greater than 0, we have conductivity, and with conductivity will be a corresponding resistance. But one thing to realize is that Ohm's law, which is quite well accepted for metal conductivity, this is really an empirical law, and I want you to remember that. For metals, we have this resistance increasing with temperature. So as you increase the temperature, because of the disorder that occurs and scattering of electrons in the material, the resistance goes up. And so remember that electron conduction in metals is due to the fact that you have this overlap of conduction and valence band. So it's very easy for valence band electrons. In fact, there's always conducting electrons in the material. So there's no change in the metal when you have current flowing through it. There's no movement of atoms or ions. It's just strictly electron motion. So if you apply an electric field, electrons move immediately in response. And I put this in quotes because there are things like the propagation of at the speed of light in order to get the electrons moving after you have applied the potential. We don't normally notice that because it takes time for example, a light switch to actually make contact. So there's really, and the other thing is speed of light is pretty small, pretty fast, so you don't see that response time. Femtosecond timescales are associated with this, and remember a femtosecond is 10 to the minus 15 seconds. Okay, so what about superconductors? These are also conductors, and they're super. There's two categories, and one is the first ones that were discovered, these low-temperature superconductors. And it turns out that several metals have this property: lead, indium, and niobium. And the what's called the critical temperature, where if you go below this, they become superconductors, are typically around 4K. So these have zero DC resistance at these temperatures. It's finite, in this case 4K. And so the DC resistance vanishes below this critical value. And so you have potentially then a way of having current, for example, transmitted across, say, wires without any heat produced in the wires. So the charge carriers in the low temperature superconductors are what are called Cooper pairs. They're paired electrons, and the theory for this type of conductivity led to a Nobel Prize. High temperature superconductors are being seen at temperatures around 77 K, but there are some that are higher now. But the two that were originally discovered to be high temperature superconductors are BISCO and YBCO. These are mixtures of compounds, so there's copper oxide and strontium and bismuth here, and then yttrium, barium, copper oxide. The delta here is on the oxygen, and in order for this to be a superconductor, you actually have to have a little bit of extra oxygen in the lattice. These are single crystals, by the way, although they can be made polycrystalline, but they're still crystals. Polycrystalline just means that the crystals are smaller than the typical object, and there's lots of them, but they're fused together so that you have the ability to still have superconductivity. The YBCO, you'll notice, is a minus delta, so you have to decrease the amount of oxygen to get this to be superconducting. Well, the high TC conduction mechanism is still a work in progress. It's very controversial, and it's pretty well accepted, though, that it involves interacting electrons, but they're not Cooper pairs. And so you'll see that this will be work that's in progress and will continue until good explanations are derived. Insulators, we've already talked about, are very poor conductors, and some examples are ultra-pure crystals of things like salts, oxides, nitrides, carbides, and polycrystalline samples. And generally when they're polycrystalline, they are called ceramics other than the salts, so oxides, nitrides, carbides. Salts are not too useful because they tend to dissolve, for example, in water, where these are robust. They have very low solubilities. So these then are used in a commercial way because they form good insulators and can do things like on your power pole keep the wires from shorting out to ground. Another type of insulator are the organic compounds, and so you're familiar with plastics or polymers. Polymer just means it's a long chain organic molecule, and of course plastics is the old term, but polymers is a little bit more modern. So some common polymers are Teflon, which is a very good insulator, PMMA, which is polymethyl methacrylate, again a good insulator, and PMMA is known as plexiglass. A number of rubbers are good insulators, and for example polyurethane is a very common and very robust material. Glasses are also insulating. We've already mentioned the amorphous SiO2, and there's several others that are used as insulators. So remember that what makes a good insulator is that you have a wide band gap and this difficulty in getting electrons in the conduction band. So we'll talk a little bit more about the role of impurities and defects in causing the pure insulators to become more conductive in the presence of those things. So I just say that like semiconductors, defects and contamination, in other words impurities, can increase the conductivity. And one thing to note is that because of entropy, at a given temperature you can have a minimum value of defect density in these pure materials. And it's just in the form of moving atoms around. So in the case of a single crystal, you can form vacancies, so you can pull an atom out of the lattice. And where might it go? Well, quite often it goes between the atoms. It's called interstitials. So good dielectrics are another example, and remember dielectrics are polarizable materials. So for example, you can put them into capacitors to increase the capacitance. And these are also insulators. Well, let's look at partial conductors, and by that we just mean in between. And semiconductors are the ones that are very useful, and you're already familiar with germanium and silicon and graphite or diamond in case of carbon. So these are generally doped on purpose with a pure dopant to make the semiconductor behave in a way that is commercially useful. If they're impure insulators made into a semiconductor by just packing impurities, then you could call it a semiconductor in the sense that it is really a partial conductor. The charge carriers in semiconductors are electrons or holes, and a hole is a site which is missing an electron, and in some cases you have both, so you have both holes and electrons moving through the material. So semiconductors have a finite DC resistance at a finite temperature, and as opposed to metals, the resistance goes down with temperature. And so this leads to some interesting behavior. So remember what we had. We had a small band gap, and this band gap is quite often referred to as the forbidden gap, because you can't have occupation of sites in here without some states. But then that leads us to this doping or impurities. Let's just talk about doping. There's two kinds. One is which gives you occupied electronic states near the bottom of the conduction band. And these would have electrons in them, so they're trapped electrons, but their energies are very close to the conduction band. So what can happen is with a finite temperature you can excite these electrons into the conduction band, and now you have charge carriers which would lead to conductivity. So when you have electrons doing this, you have a negative particle going into the conduction band, and that's called N-type semiconductors. Well, you can also have states that are down here, and they're unoccupied. There's nothing in them at the moment. But again, through thermal excitation, you can take electrons from the top of the valence band and put them into these traps. And so what happens is you leave behind what's known as a hole. And this hole is just simply a place where there's no electron. So up here it's a positive site which is missing an electron. So these energies of these holes are right near the top of the valence band. Well, let me just say that if you had holes near each other like this, and you had an electron available that can hop into this position, that leaves behind a hole. And so the mechanism of hopping between these holes, so this is no longer a hole, but then the electron can hop over here and so on. That's hole conductivity. So the electron is going this way, which means that we had minus and plus electrodes pushing it, and the holes are going this way. So they go in opposite directions. This is for what you would call hole conductivity. And that's because these are positive, it's called p-type semiconductors. Okay, so the other property that I want to just mention is that because the resistance goes down with temperature, then as you increase the voltage across a semiconductor, the current will cause heating of the material. And it's just the collisions of the charge carriers with the lattice of the material. It's a little more complicated than that. Think of phonons if you've ever heard of them. But anyway, the increase in current that occurs when you increase the voltage causes the temperature to give you more and more charge carriers, and that leads to thermal runaway. And so schematically I've shown it here where it just increases, 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 and goes out of sight. Well, that's self-destruction. The semiconductor would basically fall apart. It would melt. So in order to prevent that, you have to have current limiting circuitry to protect the semiconductor from doing this. So in other words, there's resistors and so on to keep this from happening. So defects or possibly contamination can contribute to conductivity. In this case we did it on purpose. We doped the material, but these can be there just by purchasing cheap material. But even in the purest crystal, just like the insulator, semiconductors can have a intrinsic density of defects that is temperature dependent, and these will occur in semiconductor crystals that are near perfect at least, and just thermally they produce these defects. Another type of partial conduction is ionic conductors, and I'll just briefly mention some. These are solutions which contain ions, and typically the system starts with a compound that has ionic constituents. So for example, sodium chloride. So sodium chloride, like this, has sorry for the writing here, the sodium is plus and the chlorine is minus right in the crystal. So when this dissolves, you get sodium plus ions and chlorine minus ions, and that's how you get ions into a solution typically. So when you put a voltage across the liquid, the water, for example, you'll have conductivity in both directions. So typically you have electrodes that are dipped into the solution, one with a plus and a minus, and so you'll get current through the motion of those ions in both directions. So materials which yield ions when dissolved, so for example in water, this occurs by dissociation into ions, and this is called an electrolyte if this is readily the possibility. Strong electrolytes have very high percentages of ionization. Weak electrolytes have low percentages of ionization. Now realize you can have dissolution into neutrals, and so you'd have lots of neutrals floating around in these weak electrolytes. And actually, if you have a neutral and some ions, there's basically a exchange where the neutral will dissociate, but then these would recombine. So you'd have a constant percentage of ionization. So some examples: you can dissolve salts, alkali halides. Very common is the H plus and OH plus combination, and these come from acid-base solutions. And then water itself will ionize at finite temperatures. It's temperature dependent, of course. And so you've heard of pH 7. But the 7 has to do with the concentration of the H plus and the OH minus of pure water. And so you get these ions occurring just by thermal dissociation. The presence of the ions and the conductivity of ions plays a critical role in your body. So for example, your behavior of your muscles and your brain all are dependent upon delivery and removal of ions through membranes. The whole area of electrochemistry is based on ionic conductivity. So for example, batteries, fuel cells, electrolysis where you're separating materials, and for example the production of metallic aluminum is all based on electrochemistry, which is based on ionic conductivity. There's another type of ionic conductivity, and that has to do with solids. And some solids, when you heat them up, they might be just about to melt, or even when they melt, conduct by ion motion. This is extremely dependent on temperatures, and like I say, it may require melting of the material to actually happen. So some examples are lead fluoride, silver sulfide. These have been long studied ionic conductors. Silver iodide is what's called a superionic conductor in that it has a very high conductivity once you get above about 150 centigrade. So the complex description of this conductivity is unavoidable. It's quite complex, and it often involves phase transitions, which mean that there's slight changes in the crystal when you, for example, heat it, which leads to this type of behavior. Well, I'd like to finish with this graph, which looks terrible, but let's take a look at it. What we have here is plotted the experimental band gap values, and I'll explain that in just a minute. And these are the results of a bunch of theoretical calculations. And what I want you to see is that you'll see these are columns of symbols here. What that column consists of is the value of the band gap experimentally. So this is the experimental value, and so this is for magnesium oxide right here. Lithium fluoride's way over here, and it has this column, and if you come down here, I'm just winging it here, the band gap would be somewhere between 14 and 15 electron volts. And here's your semiconductors down here, and as I said, it's below 2 electron volts for these particular values. Silicon, as I remember, is 1.1, and germanium is 0.7. Okay, so then you hire some theorists and you give them computers, and they come up with the theoretical values. And notice that there's a big range. So the pluses is one theory, and the circles is another, and the stars are another, and so on. Now, if you take a look at the full range here, you'll notice that these circles do pretty good. They cover the widest range of materials and predict a pretty close value. This line here would be, if it lies on the line, it has the same value as the experimental. And so if we compare these theories, then some are better than others, but this particular theory, it has these sets of symbols, and these crosses here, they do pretty good also. And so they have symbolic names, and you don't want to know what they are, but here they are. This whole list of letters corresponds to, okay, modified Becker-Johnson local density approximation, density functional theory, and so that's the theory that gives you the circles. And GW stands for Green's functions plus a dynamically screened interaction. It's called W. And so those two theories I think you'd find do the best, although these stars do fine down here, but then they fall apart up here. And so you can pick your theory, you can pick your theorist, and use those numbers to predict band gaps. And that's useful, for example, if you now go to impure materials, because they can do the same calculations and perhaps get the kind of band gap you want. It could be you want a particular value, that you don't want the maximum value. So that's basically a good example of a history of making calculations of band gaps and how it's evolved in terms of getting the right answer.